Okay, so welcome and good afternoon to all of you. So we are here today to talk about real-time processing with FPGAs. And my name is Matteo Collura. And I just graduated 2 months ago in nanotechnologies for micro and integrated systems. And I also have a bachelor in electronics engineering. I traveled a little bit among those universities to get my my degrees. And in the free time, I'm an amateur and passionate about IT security. So probably, or maybe you might already have checked out some of the previous researches I did in the past and presented at those conferences in the world. Regarding my last 6 months, I worked for a small company in Switzerland called Knowledge Resources. And thanks to them, I had the opportunity to develop the project that I will be speaking about today. And so without saying further ado, let's go straight to the main goals and the motivation that led me to this project. Then I will frame all the problems and why FPGAs are useful to face all the problems that are coming out. Then I will show you how to find the best configuration for the FPGAs and inspecting whether it is better to approach the problem with a processor-centric approach or with the hardware logic-centric approach. And in the end, I will explain you what is the toolbox that I developed that is implementing firewall-like features and an encryption scheme. In the end, I will provide the results and the small demos, and then I invite you to follow me at Armory in the room close to this one to get more insight and also the opportunity to discuss about the code. So the first point where I started is how we deliver confidential information in a secure way. One of the main tools that you are using is that you connect to a VPN so that you can ensure that your communication is not easily accessible by third parties that want to intercept your data. But the question that I asked is this transfer in real time? Or does it happen in real time? And the answer to this question is actually no. And to understand better this, we have to look at what is going on inside those cables here, like an Ethernet connections. I do not want to focus my research on Wi-Fi networks for obvious reasons. So I just consider the cable connections. And just take as a reference gigabit. So it is quite a common connection you have. Usually in those connections you have bytes traveling with a pace of 8 nanoseconds each because it's 1 gigabit per second. And if you're using a classic traditional computer, it's mostly referred to as a von Neumann architecture because you have a central processing unit that is all the time communicating with the peripherals like memory and network buffers. And what happens if the incoming data through your wires that are going at a speed of 1 gigabit per second are mostly comparable to the speed of the processor that is in a gigahertz. It happens that, when processing the data, there will be a bottleneck because to transfer data from the network buffer to memory and then keeping alive all the other peripherals, the processor will struggle with doing that. So how to solve this? Well, we have to consider a new, different class of devices like FPGAs that are so-called Non-Von Neumann class of devices. And in this case, for this project, I use one of those FPGAs that was produced by the company where I was working for, so Knowledge Resources. Well, one of the things that FPGAs can do very well is pipeline all the activities, and I'm sure that all of you know, what I mean when I'm talking about pipelining. But what is inside those chips? You can find several hardware logic components like logical gates, and all those components are just there, and you have to you have to build your code in such a way that you are wiring all the components that are inside. And along with the logic components, you have memory elements like the block RAM cells and also DSP logic blocks that can perform very well and very fast arithmetic operations like sum, subtractions, And the whole performance of the board depends a lot on the fabric. So how good is the electronic inside the board? And as regards the Xilinx boards, the more performances you have, the more performances on the top. And the board that I used, so the red one, is in the Kintec fabric, so it's quite, good performing. The other good thing about those boards is that you have also a dual-core processor inside. And this can be useful for a lot of reasons, and I will just be back later on this topic. So summarizing, I have an architecture where I can exploit a dual-core Cortex-A9 processor and the hardware logic that is on the board. And what I want to do is real-time monitoring the network traffic. So first of all, I have to interact with the network data. So this board itself, okay, you don't see any Ethernet interface here. So I had to use development kit to expand it. And here you can see that there is an Ethernet port just here. But what is inside this board? As I said before, you have both a processor part and the hardware logic, and the processor stays in that region that is called PS, programmable system, whereas the hardware logic stays in the PL part. To communicate from one to the other, you have to instantiate AXI bus, so the ARM bus protocols. And the only point is that the Ethernet port that I have on this carrier is directly connected to the PS part, so it's directly communicating with the processor. And you have to figure out a way, if you want to reroute all the data to the hardware logic part. So just to summarize a little bit what's going on in a network problem, you have to understand first what is the OSI reference model. So we have several layers of abstraction for what concerns network communication. And you start from the bottom, that is the physical level at the wire, let's say, level. So you're dealing with electrical signals, and then the upper level are just software abstractions. But as regards the IEEE 802.3 standard, this is mostly concerning the physical part. So how to convert the electric signals that are traveling through a wire into something digital. And my application will be mostly concerning with the lower levels of this OSI reference model. And starting from the physical medium, where you have the wire, then you get above up to the MAC controllers. So you have a couple of libraries to interact with the data from the processor side using one device like this. And these libraries are like the LWIP, that is lightweight IP, and it is good at level 3, so at IP level. And it has a dynamical allocation of memory on the chip, and this is something that I don't really like it, because if you want to implement something that is based on hardware electronics, you must always be aware of where your data are. So if you have a dynamical allocation of memory, you're not so sure about where the data will be put physically in the memory. So I decided to just discard this possibility, and I considered the other library that is more lower level. So with this library, we are interacting with the MAC controller and also the DMA, that is a very useful component to move data from the network buffer, so right after the Ethernet port, into the memory without asking any effort from the processor side. But the drawback is that it's a bit complicated to understand and to make it work. So coming back to how to route my connections from the processor side to the logic part where I do want to do the processing, I have to understand how this MAC controller, the Gigabit Ethernet MAC, works. So basically, when you receive the data from this port, you have a MAC receiver that is communicating directly with a packet buffer where you store all the packets, okay, until you have, of course, enough room. Then, as soon as one packet is received, the packet buffer will update the register, the corresponding register, and the DMA will take a bunch of those packets, one or more, and move directly to memory those packets. Then we'll update, again, the register saying, okay, the transaction is done. Of course, on the TX side is the same process. But what is the problem of this approach? First, if we consider the RX and TX buffer, they fill up very quickly. And I do not want to waste too many resources to allocate inside my board. Because when you do program something that is, on FPGAs, you do not want to run out of space or use the most as possible, because you can get other problems related to electrical interfaces when you want to drive several electronic signals. So the RX and TX buffer fills up quickly, and the packet size is always overestimated at the maximum of the packet, because you do want to be always prepared when you are receiving something that you are not expecting. Then the DMA engine is a four-state finite state machine. That means that when you do receive the packet, you are in the waiting step, then you decide to move the packet, so you are in another state, and the transition from one state to the other is regulated by the processor. So you're still keeping the processor busy along all the time of operation of the FPGA, and you do not want to fall again in the bottleneck, on the von Neumann bottleneck that I explained before. And lastly, but not leastly, the block RAM cells that I explained before that are present in the hardware logic part are not so fast in terms of speed. Well, it depends on the performance of the fabric. And too many blocks will exploit too many resources inside the board. So once again, I do not want to use a lot of them. So how can we solve this? I decided to move towards a fully hardware implementation of my design. So working just in hardware logic. And there you have, the only references you have are determined by the clock signals, and they are the only reference you have. So you must be sure that all the clock signals that you are taking into account are synchronized. And everything that you are running in hardware logic is executed in parallel. So because you are controlling electric signals, you cannot say, hey, electric signal, please stop here until I verify this condition. You cannot do that in a wire. The wire, if it is in a high state, the high state will propagate along the board without any stop, unless you put something in the middle that I will show later. And there are no libraries. So basically, you have to figure out the problem and translate it into hardware language. And these conditions lead to meeting always the timing constraints. What does it mean? If you want to route a signal from one part to the other of the board, it will take some time, because of course the traveling speed of electronic signal is influenced by the quality of the electronics you have, and it takes some time. But you do want to be prepared every time that a new clock cycle is running, as it is coming. So you want to make some stops along the ride and use a memory waypoint to carry the signal on. And the most elementary component that you have is the flip-flop, and a bunch of flip-flops are composing registers. So here is just summarized. I do hope that most of you know how a flip-flop works, but it's the simplest memory element that you have available in digital electronics. So all these things are contributing to meeting the timing constraints. So the quality of your fabric, the wire length, so the length of your connections, and the clock speed. The higher is the clock speed, the harder is to meet the timing constraints, because your signals need to reach faster than the following waypoint. So how to implement our application to monitor the traffic into an FPGA? Well, the primary goal that I decided to meet was actually building a kind of an extension cord. So like taking a piece of wire, cutting in two parts and putting in the middle this device, and ensuring that this device is able to keep the connection alive from one side to the other, and of course vice versa, because the goal is of course to keep alive the connection. And so what are the two most important points? Is first that you must ensure the continuity of data. Otherwise, if they are not continuous, the connection will be broken at some parts. And be conservative with the time of flight. This is very important. because by doing this, I'm actually buffering the whole network, and I don't want to be detectable by both the two sides of my interface. So conservative with the time of flight means that I do want not to spend too much time inside the board with my packets. So how can I interact with those data? First, I need to increase the number of Ethernet ports, indeed, to buffer all the networks, because I need two, one from one side and the other one from the other side. So I use those components that can easily be plugged in inside the board. And then, since the data flowing into a network cable is flowing when the clock signal is both transiting from the low to high state and from high to low state, so is traveling in a DDR fashion, I needed to implement a module that is converting the DDR flux into an SDR, so single data rate. And why this? Because the FPGAs run, let's say, in a better way. I can do processing easily with the SDR flux, because usually the clocks are not symmetric in the real world, and you can mess up easily with everything if you are trying to use a DDR connection. So since I'm not like a guru in this field, I decided to go for something easy like this. And if I convert to SDR, as I said before, you get 8-bit per cycle, and 8 bits per cycle means that in 8 nanoseconds, that corresponds to 125 megahertz clock, you can govern a 1 gigabit link. So how can I abstract the communication from one port to the other inside this chip? You have to think about like a conveyor belt model. So when the data enters one of the two interfaces, I'm just pushing the bytes at a fixed pace of 125 megahertz to the other side of the interface. In this way, it's as if my cable is still there. I just extended the cable because data are traveling at the same speed. And at the same time, I have these data available in my hardware platform. So these are some modules that you need to, of course, take into account. RGMII to GMII, that is the one converting from DDR to single data rate. And the PHY is the chip that you have close to the Ethernet interface that converts the data from electric signal into digital signals. Okay, so from the wire directly into a digital piece of electronic. And as I said, with a 125 megahertz clock, I instantiated a bunch of 24 registers, and what do I get from this 8 nanoseconds times 24 registers? It takes 192 nanoseconds to cross the whole board in this implementation. And if I consider the average latency that is introduced by cables when I run at 1 gigabit per second, this latency is roughly 50 microseconds. And so I'm just concluding that the time of flight inside my board is negligible with respect to the average latency. What does it mean? That if I am on one side or the other side of the board, I cannot understand whether my data were actually buffered by something that I put in between. So far, so good. So what's next? Since I have the data inside the board, now I do want to make some processing. And what I implemented were firewall-like features, then thinking about how to make some deep packet inspection, and then also, let's say, introducing an encryption decryption system to make a kind of a hardware VPN device. So let's go step by step. You know that the information travels across the wires in forms of packets. And it's like when you're sending a packet to someone, you have to provide the address of the sender and the receiver. And according to the standard defined by IEEE, so the 802.3 standard, this information has very strict specifications. And so what happens if I do not only deliver those packets, like I said before, in the conveyor belt model, but what if I introduce another element that is able to manipulate the data while they are traveling? So I have to shift my paradigm from a conveyor belt model to an assembly chain model, where I have someone that is actually able to manipulate the data while they are on the flight. And I want to be more precise about that by first introducing what is the structure of an Ethernet frame. You have at the beginning something called Preamble that is useful to for the PHY, so the chip that is below, just behind the Ethernet port, to synchronize the clock frequencies. Then it's followed by the address of the receiver, then the address of the sender of this packet. Then you have a field called EtherType that is defining the type of content. So what you have inside this packet. Is it an IPv4, an IPv6 packet, an ARP packet? Then you have the payload, that is the content of data. And in the end, a checksum field that is indicating if the transaction, just to check the integrity of the transaction. So I want to guide you through all those parts of the packets and how I processed all those parts implementing the relative features. So starting from the preamble, the board must be aware, and also you as the user must be aware of when you are receiving a packet. So you have your line that is sending you electric signal, it is in idle state, and then at a certain point you will receive this constant pattern that I was telling you, that is a series of zeros and one. And so your board must be able to detect it, and the board must be able to understand that the preamble is done. So by this pieces of code, you will see also other things like CRC engine and crypto engine, but I will talk about them later. The important thing is that by this code, that is just a elementary state machine, I'm sure that at a certain time, my packet will be inside the board because I know that I received the preamble correctly. Moving on, what do I want to do now? I want to implement a kind of a filter for the MAC address. Suppose that you want to block all the packets that are going towards, I don't know, a specific destination, like or from a specific source. Like you do want to block all the packets coming from Apple devices. Like, for example, all the Apple devices have a specific MAC address, okay? So suppose that you want to block all of them. How can you do this? You are able to detect the MAC address because the MAC address is in that specific part of the packet. And then what happens? You still do want to ensure the continuity of data. So the data must still travel on your assembly chain. But at a certain point, you can sample the data that are on the main assembly chain onto a separate belt to perform your analysis. And that's what I do here. So I sample the MAC address on a separate chain, then the data still goes through, and I can launch my search algorithm process on the steady data that I have there. So I instantiated also a blacklist inside the memory that I previously programmed, and I will be back to it later. If my MAC address is belonging to that memory, what happens? So here I find a match. Well, I simply erase all the registers that are in my assembly chain, and this will be the same as dropping the whole packet, but the packet will be lost in the board and in the wire. This is very important because the packet never gets to the end of the board, never leaves the board. And on the other side of the interface, you will be never able to understand if there was this packet or not. Because it all happens below the average latency. As I said at the beginning, it takes just 192 nanoseconds to perform all this analysis. So let's go a little bit deeper and understand what happens. I have to implement a smart lookup in memory. So all the MAC addresses will be filled inside the memory thanks to the processor that in this case is very useful because you input from the keyboard at the beginning when you're configuring your board through an interface that I will show you later. You arrange the list properly because I wanted to implement a dichotomic search, like a binary search. But in the case of the MAC addresses, to be quicker, I implemented a ternary search, and I will explain now. I do wanted to exploit a very fast component inside the board that is called DSP, and the DSP takes 48-bit entries. So the incoming MAC is 48-bit long, but to speed up, let's say the whole comparison, I decided to take just half of the MAC address size, that is 24 bits. And this allowed me to speed up a lot the process of comparison. So you could say, okay, but in this way you will miss all the specific, let's say, devices. And I can say, yes, you're right. For this proof of concept, I just decided to block like all the MAC addresses that are belonging to a specific category of device. So as I said, Apple devices have their own OUI, that is organizationally unique identifier. And these addresses are given by the IEEE as soon as you make a request for a device, like Dell computers, you go to IEEE and IEEE says, okay, for Dell devices like that, I will assign this set of MAC addresses. So the first 3 bytes are fixed, and then the other 3 bytes will indicate the device. So my filter will operate, for now, only with the first 3 bytes. But let's see how this search algorithm works. As I said, it's a ternary search algorithm. So I do want to compare 2 entries per time. And what I do is simply making a subtraction and checking the sign bit. So taking the MAC from the network, subtracting the MAC that I stored in memory, and then checking the sign bit. If that holds, I mean, it always leads to discrimination of 2 groups out of 3. So the third group will be furtherly inspected in the same way. And the whole process can be summarized with this state diagram. And it takes always the same time to be executed, because I know that by ternary dividing every time a set of 80 elements, I will come to just 1. And if this one is still not belonging to the memory, that means that my entry that I found from the network is not belonging to memory, so it could go through. So how to configure this? I will introduce now a small demo that I prepared. First, this is the interface that you will see from the computer when running this software. And there are, as I said, you can input up to 81 entries. That is corresponding to 3 to the power of 4 because of my ternary division algorithm that takes, as I said, just 4 cycles to be done. Well, the 5th cycle is important as well. And then you have to indicate whether you are filtering source MAC addresses or destination MAC addresses or both. So this is the setup. I had 2 workstations, one connected to the first interface, the other to the second interface. I was generating some traffic with workstation number 1 and receiving that traffic on the workstation number 2. So you can see from here, sorry for the video quality that is not so good, but I hope you can still enjoy it. So here I'm indicating this code that is corresponding to the Apple unique identifiers, because I hate Apple, but that is another story. And I confirm my blacklist here, and I just launched the interface, and here I'm generating some traffic. The first is coming from a Xilinx device and is directed to a generic device. This 58E287 that you see here indicates a generic device. And here, following, you will see that I'm also generating packets that are directed to Apple device. Well, that are generated by, Apple devices. And this traffic is routed to my secondary machine here. And as you can see, the first one are correctly delivered, but there is no evidence of any trace of the following packets from Apple. So here I included a different screenshot from Wireshark. I was using another pair of MAC addresses, and I was filtering the Xilinx one. So you can see that there is a one-to-one correspondence with the elements that I pointed with the arrows, but there is no trace regarding the others. And so summarizing, what did I get from this? I just need 80 nanoseconds to browse the whole memory and find if the MAC belonging to it. And this is improvable to 64 nanoseconds because I messed up something with the algorithm, but you can trust me that it is improvable to that. I can tell you later in Armory if you just drop by. The process ends always on the same checkpoint. And this is important. As I said at the beginning, you must be always aware of where the packet is inside the board. And since you know that the process takes always the same amount of time to run, you know that 10 bytes are entering the board while you are processing the MAC filter. So I know exactly where the packet is inside my board, and this is very important. So I can go and move on. And now face the EtherType. I decided to implement kind of the same algorithm to filter the EtherTypes. So in this case, for example, I didn't want to let through all the IPv4 packets. Let's say I do not want any IPv4 packet to go through the board. So the algorithm works in the same way. You store first the blacklist entries inside the memory, you sort them, and then the board will take care of the whole process by just dividing the set of entries that you have in memory up to the single element. And this time, this is a binary search algorithm, but where I'm checking 2 entries per time, because the EtherType is just a 2-byte field. So since the DSP is able to process up to 48-bit variables, I decided to put just 2 because they were fitting. Then, okay, we can skip this. If you have any additional question on the differences between the 2 algorithms, as I said, since it will be mostly technical, you can keep for later, or I will be glad to answer. So let's come now to the payload. What did I do on the payload? As I said, I decided to implement an encryption environment to build what is a kind of a hardware VPN device. Because if I'm able to encrypt the data in real time, do you remember the first problem that I showed you, that when I was considering VPN, I said, is it real time? And this time I want to make it real time, because as you realized probably up to now, I'm able to make the whole process in less than 0.2 microseconds. And since it is undetectable by other sources, I consider this as a real-time equivalent. So what did I do? The interface is very simple. The user is requested to input a password, and from that password, the board will generate the keys that are required to encrypt the data while they are traveling. And the scheme is really, really simple. So you are still receiving the data and you want to ensure the continuity of data, as I said before. So when they are traveling, you do want to sample on a separate chain this data. So this data are still going through, but this time on a separate belt, you have the logic that is performing the encryption of the data. So at this time, you have both the original version of the data and the encrypted version of the data. So what can I do to just substitute the original with the encrypted one? I will use a multiplexer that takes the encrypted version and replaces with the original in this way. So the data will be modified on the flight. Okay? Regarding now the more detailed part regarding the encryption system, I first put this disclaimer because I'm not a crypto expert, and just to make these proof of concept devices, I do not really invest a lot of time to build up a very strong and robust security algorithm, so please don't blame me for that. Without saying more funny stories about that, I will show you how it works. Basically, from the password that the user inputs, I will generate a 32-bit hash. Yes, it's very low, but I mean, it's very small, this hash, but I need it because I have to process 1 byte per time. So to make it more secure, I just take subsets of these data, 8-bit subsets, and it works in this way. You have the password input by the user, you generate the hash, And then this is handled by the processor that has still the computing power that you need to generate hashes very quickly. But then what happens? These data must be communicated to the hardware logic platform. And to do this, I simply instantiated a channel of communication that is delivering the whole hash into the hardware platform and stores into a bunch of registers. Now, to support this cycling of the keys, I mean, I'm generating first a big key, and then I'm taking subsets of this key to have multiple keys. I'm just cycling through like this, taking subsets. And this is done by cycling the data inside the registers, connecting them in a ring shape. And so it's as if you have this situation. And this goes on along with the clock, the main clock, and along with the data that is coming through. And what happens? From this subset of 8 bits that are variable, I just, okay, yes, it's a symmetric operator, the simplest one that I could use, but it's a proof of concept device, I will say once again. And using this hardware in this way, I can use the same hardware for both encrypting and decrypting because it's a symmetric operation. So there is only one thing missing now. How can the board distinguish from the original packet, so the plain text version, and the ciphered version? Because in this way, I'm encrypting all the payload, but how can the board decide whether to accept the packet or decrypt it first? So I need to put some signature somewhere. And I want to first put some requirements that I need. And I do want to preserve the size of the packet. So I do not want to enlarge the payload to include the signature, because otherwise on the other side of the interface you can detect that packets have different sizes, and I do not want to do this. Of course, the checksum will be recomputed. Otherwise, it will result in a packet failure because the checksum is wrong. So maybe the following interface will not accept the packet. And lastly, but not leastly, the MAC headers should be preserved. Otherwise, you cannot deliver correctly your packet to the following endpoint. So no way to include the signature in the preamble. Otherwise, the board will not be able to detect the packet. No way, of course, to include in the MAC because I explained you. The payload is already encrypted and could not be enlarged. So once again, no way to use that. The checksum could be manipulated actually to include a signature, but once again, it will be hard for another interface to accept the packet because it will be considered as malformed. So the only missing part is the EtherType, that is containing the information related to the protocol. So what is inside the packet? And this field is not containing values. I mean, all the values that you can put there are not already assigned. The IEEE, once again, decides whether to assign to a specific protocol a corresponding EtherType. So what did I decide to do? Just taking the first EtherType and generating, well, not generating, just inspecting the list. And if there is a non-assigned EtherType, just matching with the original EtherType and changing that. So by changing the EtherType, I'm able to let the board understand whether the packet is encrypted or not. And I did take the IPv4 code that is 0800, and using this network of hardware logic components, I will be able to modify on the flight this value into a custom value. And this will be done thanks to those multiplexers. When you see them in red, it means that they are taking the low connection, so the red one, and if they are turning into blue, they will accept the upper one. So what happens? The data are entering. I know, since I told you before, I always know the position of the bytes of my packet inside my pipeline. So I do want to trigger those multiplexers only when the 08 is going to be placed in this register, and when the 00 is going to be placed in this register, because in this way I can take the corresponding encrypted versions and let them through. So right now it's still red because it's not the desired situation, but here it becomes blue. So I get here the custom generated number, and it will be pushed through the whole network. So in the end, I will have a packet with a different EtherType ID, and with the encrypted version of the payload that I generated before. In the end, the board will automatically detect and decrypt the packets. Why? Because if the board finds this custom EtherType, it will understand immediately that the packet needs to be decrypted, and the hardware will be the same, as I said before, because the operators that I use to encrypt are symmetric. So I show you another demo now. It's concerning the encryption part. So the setup is kind of the same as before, because I want to show you the payloads of all the packets that I'm generating. So the task workstation 1 will generate some traffic and push through the first interface. Then the data will leave from the second interface and will be accepted gladly by the second workstation. And so the user will have to input a password, as I said before, and choose what is the port, I mean, among those two ports, which is the one that is connected to the external world, because actually you do not want to encrypt the data that are coming to your machine, for indeed. So here you have it. Sorry for the video quality once again. So the first machine here, I'm inputting now the password. I choose first the external port. So here I input the password. The system will generate the keys. And now here, once again, I'm generating this traffic. Once again, you will see this Apple tag. But you can see as soon as I click on, as soon as I click on the packet, you will see the payload. So the payload is just incremental. You will see here, you see that all the bytes are incrementing, so it's easy to be read there. And this is the original traffic. Whereas on the other side, I'm moving here. As you can see, I received those packets. And if I click on them, you will be not able to distinguish anymore the incremental pattern. All was encrypted, and you can see that the headers were the same, because you could distinguish at the beginning Apple and Xilinx were still there. Here, this field here, you can see the custom number that I assigned to my encrypted packet. And then here the payload is all this way. So I included also here to match the two that are different, of course. And I included as well, screenshot of, once again, what you will find. So here the incremental bytes, and there you will see the encrypted version. And once again, I stress your focus on the EtherType that is different. And you can see also from the user interface. So from protocol, you see first IPv4, and there you don't see anything, because Wireshark do not know what is this protocol, because it's still not assigned by IEEE. And of course, I do included a demo that is showing you that is, of course, indeed possible to decrypt this data. Otherwise, it will be not so useful. The setup is a little bit more complicated, but I will guide you through. The test workstation is generating traffic for this board labeled B, and the board labeled C is actually repeating back all the packets that is receiving. It's just a mirror, and it is connected to this other interface here. So what's going on now? The machine A generates a plain text traffic and sends out of the board. Then this traffic will reach the board B. The board B will encrypt the plain text, will generate the ciphertext, and will push it out of the interface, and it will reach the board C. The board C, as I said, will only loop back the packet, just mirroring it back. And so you will have the same packet. And finally, the board B will receive the encrypted packet, and of course will detect that the packet is in the encrypted form and will decrypt the payload. So hopefully, in the end, the board A will be able to receive the plain text version once again. So what are you expecting now? You're expecting to see from Wireshark that when you're sending out a packet, you will see a copy of the same packet following immediately. And this is what I want to show you now here. I have once again this setup as I shown before. I will generate once again the keys after inserting the password, and so here I will generate the traffic from the interface. Yep. Okay. So here you see that. Okay. For each packet, you find a duplicate of the same for the reasons that I told you before, because the packet is reaching the other board and gets back, and the board is able to decrypt it. But from here, it's not possible to see whether the payloads are the same. So I will just open the packets, and you will see that the first one is the usual incremental bit fashion, and the following is the same, exactly the same. And so this is proving that the whole encryption and decryption system is working. And okay, so what's left? We have to recompute the checksum, because otherwise those packets will not be accepted. So the process is kind of the same. Now you got the main line, so you have to sample the data while they are traveling, and the CRC logic is actually working by taking and inspecting each byte. So you have to feed this CRC logic with each byte that is belonging to the transaction, and then it will generate a 32-bit entry that will be the CRC32, of course. This indeed must be placed after the encryption architecture, because otherwise you will sample wrong data. And yeah, the code that is governing the two multiplexers is basically, there are two variables that are: the first, CRC append, will indicate when the packet is over. So when the CRC must push their data in the line, so injecting the new created CRC32 in the pipeline. And instead, the other one is crypto detected, is a variable that indicates whether the board recognized correctly this custom tag I created, and it is operating on the first multiplexer there, so selecting the ciphered payload, or in this case, the ciphered payload, or the main one. So as regards to the checksum, as I said, the CRC logic will push in those registers the 4 bytes that are composing the checksum, but at a certain point, you have to push inside the main chain, the main pipeline, those 4 bytes, and append them to the end of the packet. So that's pretty much it as regards the level 2 analysis of this packet. But what's next? This will be under development for the future, let's say, of this application. But I started already inspecting what happens at level 3. So you need to let's say, look inside this payload block that is containing all the upper levels, level 3, 4, and so on. So IP, TCP, etc. So I started inspecting this. When you ping someone in the network, you're actually sending out an ICMP packet, right? So inside the payload, you will find this indicator that is indicating the protocol is the ICMP, and it is located just 10 bytes after the EtherType here. So what if I have my packet through the board and I detect that exactly this configuration, IPv4 here and the protocol here that is corresponding to ICMP, so like this situation. Well, if I enable this feature, it means that I can remove my white hat and put the black hat on, and I can say that I can connect my computer to the network and drop all the ICMP's requests that are towards my computer. That means that I can generate a device invisible to the network, right? So that's one of the dreams of every black hat, right? Moving on apart this story. So what were my achievements so far? I achieved transparent modification of my data. As I told at the beginning, the data are modified while they are transiting through the board. This is very important. I do not require any additional delay for the processing, because I can pipeline the process of delivering the data from one side to the other of the board, and at the same time processing the data. So that's why I called it real-time equivalent, because in the end, when the packet leaves the board, it's in a completely new fashion. So it could be encrypted, or it could even not exist anymore if I drop it along the line. Then pipelining allows multiple firewall feature implementations. And I showed you that I can implement a MAC filter, both for source and destination address. I can implement a EtherType filter, so the protocol filter. I can drop all the ARP requests, the IPv4 request, and so on and so forth. But I will extend in the future with IP, for example, address firewalls. Like you can block certain IPs in a certain range, and the process will be the same as the other that I explained before, and they can be run together at the same time. Then the whole time of flight, I remind you, that takes just less than 0.2 microseconds. And this is well below the average latency that is introduced by a wire and a connection that is running 1 gigabit per second. So overall, you cannot distinguish whether you are tapping the network. That is what I'm doing. I'm tapping the network. You cannot be able to distinguish that. And lastly, the point-to-point encryption that I established, okay, right now it's not so secure, it's not strong, let's say, but in the future I will enable the encryption not 1 byte per time, but a bunch of bytes per time. So maybe I can even introduce SHA-256 key inside the board and use this to encrypt a whole bunch of data. And this is easily scalable. So as regards to future upgrades, as I said, the filter can be extended to upper layer protocols like IP, and it will be for sure done in the future. So filtering the IP addresses and so on and so forth. And then introducing the packet inspection. Like you can set up a lookup for a certain word inside the payload and apply the same principle for blocking the packet before it leaves the board. And the only problem with this, it is that it's not so easy to implement, let's say, so generic filter for a custom word inside a hardware logic platform, because programming hardware is very different from programming software, and what you gain is that you can do all those things, so process data that are incoming at high speed in a real-time fashion, but what you lose is that if you want to create something flexible, you will struggle a lot. And but anyway, I will find a way maybe for the future research, and hopefully presenting maybe in the future what will follow after this. So I hope that everything was clear to you, and I hope you have also some questions for me, and I will be very glad to answer. So I would like to thank you for your attention, and yeah, you can follow me on LinkedIn, and so yeah, that's it. Thank you.
Thank you very much, Matteo. Are there any questions from the room? No, I think Matteo will be around. Some more. So if there are questions later, people might want to ask you.
Yeah, there is one question there.
Oh, there is. Oh, sorry. Sorry, I totally missed that.
Thank you so much for this lovely presentation. I just would like to know regarding the CRC calculation.
Sorry?
Regarding the CRC calculation for checksum.
Yep.
So since you have multiple registers, so you are calculating the CRC value at the end of the last register. This is what you are trying to do? Yeah, the CRC.
This one?
Yes, exactly.
Okay.
So you have multiple registers. So obviously the traffic is passing through those registers. So you are calculating the CRC based on the complete formation of the packet or each bit by bit?
So to evaluate the CRC, you need to push inside the logic all the packets starting from the beginning. So this unit is actually taking in all the bytes since the beginning of the packet. And it terminates acquiring all those bytes as soon as this flag is raised. So the CRC append will stop the acquisition of the CRC logic and will, from here it's better, because here the CRC logic will update the value inside those 4 registers that are corresponding to the 4 bytes of the CRC. And as soon as this CRC append is raised, this connection will be multiplexed with the other one, and the new CRC will just will be pushed in the main line. So what happens now? The new CRC will be multiplexed here. So I will just select the one coming from here, and the real CRC, well, the original one that was stored here, 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 and the previous one will be lost, because here it will be replaced by those 4 bytes. So they will come here, 1, 2, 3, 4, and then the packet will be pushed out.
If I understood it correctly, you put the what you call signature into the EtherType, but I guess going forward, if you use the larger size signature, like 256-bit, it's not going to fit. So do you have a plan there? Is it going to result in fragmentation or other plan?
Yeah, I use this word signature, actually not meaning the true, I mean, what is commonly used as signature, that is a custom like ending of the packet, that is verifying that the whole thing is just generated by a user with a specific credentials. Okay, so this signature was kind of an identifier to detect. I mean, from the board side, you must be sure that this packet was encrypted by your algorithm. And I'm well aware that this is not actually a strong. Well, it's not a signature in the true sense. It's more like a way for the board to detect that the packet was treated by the board itself. So, as I said, I'm not a crypto expert, so I could mess up easily with those terms. But based on the requirements that I shown, so that I do not want to increase the packet size, otherwise it will not be a transparent modification of data. I do not find at the moment any other place where to put this unique value. So feel free to give me suggestions, or just let's have a talk, maybe a conversation later about that, because that will be really useful. And up to now, I didn't find any place where to add this unique value.
Are there any other questions? No? All right. Matteo, thank you so much.
Yeah, just want to add just 10 seconds. So if you want to enjoy with programming those boards, just feel free to check the website, also the company that produces this, and I will give you the details later. So you can play with those boards as well, and you can program it without any other expenses, because you don't need licenses to program on those boards. So that's fine. So I want just to say this to conclude. So thank you for your attention once again, and thank you for letting me here.
No problem.